For the last 10 years, I've been spending my time trying to figure out how and why human beings assemble themselves into social networks. And the kind of social network I'm talking about is not the recent online variety, but rather the kind of social networks that human beings have been assembling for hundreds of thousands of years, ever since we emerged from the African savanna. So I form friendships and coworker and sibling and relative relationships with other people who in turn have similar relationships with other people, and this spreads on out endlessly into a distance, and you get a network that looks like this. Every dot is a person, every line between them is a relationship between two people, different kinds of relationships, and you can get this kind of vast fabric of humanity in which we're all embedded. And my colleague James Fowler and I have been studying for quite some time what are the mathematical, social, biological, and psychological rules that govern how these networks are assembled, and what are the similar rules that govern how they operate, how they affect our lives. But recently, we've been wondering whether it might be possible to take advantage of this insight to actually find ways to improve the world, to do something better, to actually fix things, not just understand things. So one of the first things we thought we would tackle would be how we go about predicting epidemics. And the current state of the art in predicting an epidemic, if you're the CDC or some other national body, is to sit in the middle where you are and collect data from physicians and laboratories in the field that report the prevalence or the incidence of certain conditions. So-and-so patients have been diagnosed with something, or other patients have been diagnosed, and all these data are fed into a central repository with some delay. And if everything goes smoothly, 1 to 2 weeks from now, you'll know where the epidemic was today. And actually, about a year or so ago, there was this sort of promulgation of this notion of Google flu trends with respect to the flu, where by looking at people's searching behavior today, we could know where the flu, what the status of the epidemic was today, what's the prevalence of the epidemic today. But what I'd like to show you today is a means by which we might get not just rapid warning about an epidemic, but also actually early detection of an epidemic. And in fact, this idea can be used not just to predict epidemics of germs, but also to predict epidemics of all sorts of kinds. For example, anything that spreads by a form of social contagion could be understood in this way. From abstract ideas on the left, like patriotism or altruism or religion, to practices like dieting behavior or book purchasing or drinking or bicycle helmet, other safety practices, or products that people might buy, purchase of electronic goods. Anything in which there's kind of an interpersonal spread, a kind of a diffusion of innovation, could be understood and predicted by the mechanism I'm going to show you now. So as all of you probably know, the classic way of thinking about this is the diffusion of innovation or the adoption curve. So here on the y-axis we have the percent of the people that are affected, and on the x-axis we have time. And at the very beginning, not too many people are affected, and you get this classic sigmoidal or S-shaped curve. And the reason for this shape is that at the very beginning, let's say 1 or 2 people are infected or affected by the thing, and then they affect or infect 2 people, who in turn affect 4, 8, 16, and so forth, and you get the epidemic growth phase of the curve. And then eventually you saturate the population. There are fewer and fewer people who are still available that you might infect, and then you get the plateau of the curve, and you get this classic sigmoidal curve. And this holds for germs, ideas, product adoption, behaviors, and the like. But things don't just diffuse in human populations at random, they actually diffuse through networks. Because as I said, we live our lives in networks, and these networks have a particular kind of a structure. Now, if you look at a network like this is 105 people, and the lines represent, the dots are the people, and the lines represent friendship relationships, you might see that people occupy different locations within the network. And there are different kinds of relationships between the people. You could have friendship relationships, sibling relationships, spousal relationships, coworker relationships, neighbor relationships, and the like. And different sorts of things spread across different sorts of ties. For instance, sexually transmitted diseases will spread across sexual ties. Or, for instance, people's smoking behavior might be influenced by their friends, or their altruistic or their charitable giving behavior might be influenced by their coworkers or by their neighbors. But not all positions in the network are the same. So if you look at this, you might immediately grasp that different people have different numbers of connections. Some people have 1 connection, some have 2, some have 6, some have 10 connections. And this is called the degree of a node, or the number of connections that a node has. But in addition, there's something else. So if you look at nodes A and B, they both have 6 connections. But if you can see this image from a bird's eye view, you can appreciate that there's something very different between nodes A and B. So let me ask you this. I can cultivate this intuition by asking a question. Who would you rather be if a deadly germ was spreading through the network? A or B? B. It's obvious. B is located on the edge of the network. Now, who would you rather be if a juicy piece of gossip were spreading through the network? A. And you have an immediate appreciation that A is going to be more likely to get the thing that's spreading and to get it sooner by virtue of their structural location within the network. A, in fact, is more central, and this can be formalized mathematically. So, if we wanted to track something that was spreading through a network, what we ideally would like to do is to set up sensors on the central individuals within the network, including node A, monitor those people that are right there in the middle of the network, and somehow get an early detection of whatever it is that is spreading through the network. So if you saw them contract a germ or a piece of information, you would know that soon enough, everybody was about to contract this germ or this piece of information. And this would be much better than monitoring 6 randomly chosen people without reference to the structure of the population. And in fact, if you could do that, what you would see is something like this. On the left-hand panel, again, we have the S-shaped curve of adoption. In the dotted red line, we show what the adoption would be in the random people. And in the left-hand line, shifted to the left, we show what the adoption would be in the central individuals within the network. On the y-axis is the cumulative incidence of contagion, and on the x-axis is the time. And on the right-hand side, we show the same data, but here with daily incidence. And what we show here is like here, very few people are affected, more and more and more up to here, and here's the peak of the epidemic. But shifted to the left is what's occurring in the central individuals. And this difference in time between the two is the early detection, the early warning we can get about an impending epidemic in a human population. The problem, however, is that mapping human social networks is not always possible. It can be expensive, not feasible, unethical, or just frankly, just not possible to do such a thing. So how can we figure out who the central people are in a network without actually mapping the network? So here what we came up with was an idea to exploit a very old fact, or a known fact about social networks, which goes like this. Do you know that your friends have more friends than you do? Your friends have more friends than you do. And this is known as the friendship paradox. Imagine a very popular person in the social network, like a party host who has hundreds of friends, and a misanthrope who has just one friend. And you picked someone at random from the population, they were much